Good morning. Today we will discuss in detail about semiconductors. We will see some of their characteristics and what are the different kinds of semiconductors and all those details. So, what are the peculiar characteristics of semiconductors? One important property is that their conductivity increases when impurities are mixed with them. This is not seen either in insulators or in metals or conductors. If we add the impurity, there is no much effect on their conductivity. So this is a peculiar property of semiconductors. We will later see in details what happens when which kind of impurity is added to them. So this is one of the peculiar property of semiconductors. Then we say that at absolute zero temperature, they are insulators. So here you can see the picture of energy band of a pure semiconductor. Pure semiconductor, which is also called an intrinsic semiconductor, behaves like insulator at T is equal to 0 Kelvin. That is, the absolute temperature is 0. So when the absolute temperature is 0, all the electrons in the atom of a pure semiconductor will be in the valence band. In the last class, we saw that there is a small gap between the valence band and conduction band of a semiconductor. And this band gap or forbidden energy band is less than 1.1 electron volt. So electron here needs at least 1.1 electron volt to jump to a conduction band and conduct electricity. So at absolute zero temperature, there are no energy available for the electron to jump to the higher energy level. So at absolute zero temperature, they behave like insulators. Now, their resistance decreases with increase of temperature. Resistance decreases means the conduction increases. So let us see what happens when we increase the temperature of the pure semiconductor. Here you can see at temperature higher than 0 Kelvin, what happens? Thermally generated electron hole pairs are formed. So if you increase the temperature, the electrons which are in the valence band, they will get some temperature. So they will get some energy. They will get some energy. So what happens? They will jump to a higher energy level. So the electrons here will jump to higher energy level because when we increase the temperature, the kinetic energy of the electron increases. So they will receive some more energy. Suppose this is a germanium atom. Germanium have the band gap 0.7 electron volt. So if an electron here gets a kinetic energy due to the applied temperature greater than 0.7 electron volt, they can jump and they can get into the conduction band. So the electrons are now available in the conduction band and therefore they can conduct electricity. So this is what will happen when we increase the temperature. So as they can conduct electricity, now electrons are available in the conduction band, their resistance decreases. So this is a property of semiconductors. When we increase the temperature, the resistance decreases. Do you know what happens to metals when we increase the temperature? Do you have any idea what happens in metals when we increase the temperature? What happens to their resistance? For metals, when we increase the temperature, their resistance also increase. Why? Because in metals, there are more free electrons available. So if we increase the temperature, they will move randomly and they will hit each other, collide each other. So if they are at a lower temperature, when we apply the electric potential, the free electrons can carry them smoothly. But if we increase the temperature, what happens? Because of the higher temperature, their kinetic energy will increase. There will be more frequent collision. So they cannot freely conduct electricity as they did in a lower temperature. So their resistance increases. So this is one point which you have to note. For metals, when we increase temperature, their resistance increases. But for semiconductors, when we increase temperature, their resistance decreases. So it's opposite for metals or conductors and also for semiconductors. Their property is different. Is that clear to you? Is that part clear to you?
Yes, teacher.
Okay.
Yes.
Now, for pure semiconductor, electrical conductivity increases either with the rise in temperature or by the rise of the applied potential. Suppose they are in low temperature. The applied temperature cannot provide how much electricity is, sorry, 0.7 electron volt energy to the electron. Suppose the temperature is not that high. In that case, if you are applying a potential, when you apply potential, the electrons are given some electrical energy. If that is above this potential barrier, this band gap, maybe they get about 1.2 electron volt energy by the applied potential, then also they can rise to the conduction band and conduct electricity. So there are two ways by which we can increase the conductivity of a pure semiconductor. One is by rising the temperature or by the rise of the applied potential. There is a third method by which we can increase the conductivity of semiconductors, that is by adding the impurities. So these are the three ways by which we can increase the conductivity of semiconductors. But by increasing temperature and also by increasing the potential, there is a limit to which we can increase the conductivity, because there will be available only few conductors and the conductivity will be very low. The resistance will be still high. So the best method to increase the conductivity of semiconductors is by adding impurities. Here you can see silicon and germanium. These are uh, usual atoms having less number of electrons or 4 electrons in their outermost shell. So these are elements or atoms which act as pure semiconductors, silicon and germanium. Germanium has a band gap of 0.7 electron volt and silicon has a band gap of 1.1 electron volt. So either by increasing temperature or by applying enough potential, we can rise their conductivity. Now, what happens when we add impurities to semiconductor? When we add impurities to semiconductor, holes and electrons are the two types of charge carriers which are produced in the semiconductor, and they are responsible for current in semiconductor. What is a hole? Hole is a new concept which is available for conduction only in semiconductors. We do not have holes available for conduction in metals or conductors. So what are these holes? A hole is the absence of electron in a particular place in an atom. See here, if an electron jumps to a conduction band, there is a vacancy of electron available in the valence band. This is called a hole. So this is the absence of a electron or vacancy of a electron in a particular place. So it acts like an electric charge carrier with a positive charge. Why this acts like a positive charge? Because this is a vacancy. If there is an electron in a neighboring atom, it can jump to this position and occupy this vacancy. So if an electron moves from right to left, the hole moves from left to right. The other atom will have that vacancy there. So this hole moves in a direction opposite to that of an electron. That is why we call that it acts like a positive charge. So it's not a positive charge, it is neutral, it's not positive charge, it's just the vacancy of an electron. But since it moves opposite to the direction of electrons, we call it behaving like a positive charge. And also it's a vacancy, so it will attract the electrons in the neighboring atoms. Oh, that is also another property of a positive charge. So they behave like a positive charge, and they behave as if they have equal charge, equal in magnitude but opposite in polarity to charge of an electron. So they behaves like a electron having positive charge, that they have a charge 1.6 into 10 raised to minus 19 coulomb, which is same as the magnitude of charge of an electron, but they behave like a positive charge. So is that clear what is a hole? Is that clear
Yes.
what is a hole? Yeah, okay. So you may be asked a question, what is a hole? So you have to tell that holes are, a hole is the absence of an electron in a particular place in an atom. It acts like an electric charge carrier with a positive charge, equal in magnitude but opposite in polarity to the charge of an electron. So it behaves like a positive charge. Actually, it is not positive. But since it attracts electrons from other atoms and it moves in the direction opposite to that of electrons, it behaves like a positive charge. So are the characteristics of semiconductors clear to you? Are the characteristics of semiconductors clear to you?
Yes, teacher.
Yes.
Okay, so let us see the classification of semiconductors. So the semiconductors are broadly classified into intrinsic semiconductors and extrinsic semiconductors. What are intrinsic semiconductors? Pure form of semiconductors are called intrinsic semiconductors. And what are extrinsic semiconductors? Impurity added semiconductors are called extrinsic semiconductors. Extrinsic semiconductor, depending upon the kind of impurity added, again can be classified into N-type semiconductors and P-type semiconductors. We will see that in detail in this class, but before that, let us see the properties of intrinsic and extrinsic semiconductors. So, semiconductors can be broadly classified into intrinsic semiconductors, which are pure semiconductors, and extrinsic semiconductors, which are impure semiconductors. The semiconductor to which no impurity is added is called an intrinsic semiconductor or a pure semiconductor. Atoms of the fourth row of periodic table, carbon, silicon, germanium, tin, etc. are examples of intrinsic semiconductor. All of them, carbon, silicon, germanium, tin, all of them have 4 electrons in their valence shell. This is the peculiarity. All of them lie in the fourth row of the periodic table. Carbon have 4 electrons in its outermost shell. Similarly, silicon has 4 electrons, germanium has 4 electrons, tin also has 4 electrons. So all these atoms behave like intrinsic semiconductor, and the number of electrons is equal to number of holes in an intrinsic semiconductor. Why is it so? Because here we saw that in an intrinsic semiconductor, the electron from the valence shell jump to the conduction band. So from the valence band, jump to the conduction band. So when one electron jump to the conduction band, one hole is formed. So if another electron jump to the conduction band, another electron hole is formed. So how many electrons are formed here? Four. So how many holes are formed here? Four. So in an intrinsic semiconductor, the number of electrons formed will be equal to the number of holes, because number of free electrons are formed due to jumping from the valence band to the conduction band because their temperature is increased. So number of electrons is equal to number of holes. Is that clear to you? How in an intrinsic semiconductor, the number of holes becomes equal to the number of electrons? Is that clear?
Yes, teacher.
Okay. And the number of charge carriers are less. So the conductivity is less. As I told you, by increasing the temperature or by increasing the potential, we can create only few electron hole pairs. We cannot create more of them. So for an intrinsic semiconductor, the conductivity usually is very less. So what we do to increase the conductivity of semiconductors, we add impurity to them. And then we call those semiconductors extrinsic semiconductors. So for most of the commercial purposes, to make many of the semiconductor devices, we use extrinsic semiconductors. Extrinsic semiconductors are impure because some impurity is added to the pure form of silicon or germanium or any other compound which we use as a semiconductor. So extrinsic semiconductors are impure semiconductors, and a huge number of charge carriers can be produced by the impurity. So the conductivity is very high, and also by adjusting the amount of impurity added, we can adjust the conductivity of such semiconductors. So semiconductors, especially the extrinsic semiconductors, are widely used in producing most of the electronic devices. So this addition of impurity in a semiconductor is called doping. So what is meant by doping? The addition of impurity to a semiconductor is called doping. And we can adjust the amount of impurity added. So we can get the required amount of conductivity for the material. So this is widely used and very useful when we are using new devices or when we are inventing new devices. And in an extrinsic semiconductor, the number of electrons and holes are not equal. When we discuss the N-type and P-type semiconductor, you will see why in an extrinsic semiconductor, the number of electrons and holes are not equal. Is that clear? What are intrinsic semiconductors and what are extrinsic semiconductors?
Yes, teacher.
Okay, now we will focus on extrinsic semiconductors. We will see further classification of extrinsic semiconductors. They are classified as N-type and P-type. Like when we add a pentavalent impurity. Pentavalent means what? What is meant by penta? Which number does it stand for? Penta. Penta means 5. So pentavalent impurity means impurity having 5 electrons in their valence shell. Pentavalent means having 5 electrons in the valence shell. So if we are adding such elements. The examples for such atoms are phosphorus, arsenic, antimony. P for phosphorus, A is for arsenic, and SB for antimony. So if you are adding such impurities, we get a N-type semiconductor. They are also called donor impurity, and the number of electrons will be much more than the number of holes. And in p-type semiconductor, we are adding a trivalent impurity. What is meant by tri? You will be familiar with tri.
Three.
Tri means three.
Three.
So how many electrons will be there in the valence shell? Three electrons.
Three.
Yes. So if the number of electrons in the valence shell are 3, we call them trivalent impurity. And examples for such elements are gallium, boron, indium, aluminium. So if these metals are added to pure semiconductors like germanium or silicon, we get p-type semiconductor where the number of holes are much more than the number of electrons. So let us see how we can make n-type and p-type semiconductor by adding pentavalent and trivalent impurity. What happens? So here we is given the classification or the difference between n-type semiconductor and p-type semiconductor. What is an n-type semiconductor? It is an extrinsic semiconductor which is obtained by doping the impurity of pentavalent impurities. I think there is a mistake in typing here. By doping pentavalent impurity atoms such as antimony, phosphorus, arsenic, etc. to the pure germanium or silicon semiconductor. So here, this is silicon. Si means silicon. Sb means antimony. So here we have an example of silicon. In silicon, we know that there are 4 valence electrons in their outermost shell. So when you take a crystal of silicon, there will be 4 valence electrons and they will share with a neighboring silicon electron these 4 valence electrons. So what happens? There will be 8 electrons as a whole. So all of the neighboring silicon atoms will share 4 of their valence electrons with the 4 neighbors so that the octet or 8 electrons in the outermost shell is complete. That is how they exist in the crystal of silicon. Now, if you are adding antimony, Sb, to this crystal, what happens? Antimony is pentavalent. It has 5 electrons in its outermost shell. So it will share the 4 electrons. See, one shared here, one shared here, one shared here, one shared here. Then there is one extra electron available for antimony, but this electron cannot be shared with anyone. But antimony already had 8 electrons now because of the sharing of electrons by the neighboring silicon atoms. So its octet is complete. So this extra 5th electron which it had is now free. So it contributes as a free electron. So this antimony donates one free electron to the crystal. So it is called a donor impurity. So it donates an electron. So this is available as a free electron. So when you add some impurity to the crystal, you will be adding large number of impurities. For example, 10 raised to 8 electrons, 10 raised to 8 atoms are added. So when to a crystal structure, we learned in the last class that there are around 10 raised to 23 atoms per unit volume. So to that, if we add some impurity, maybe 10 raised to 8 atoms, then what happens? We will get 10 raised to 8 electrons free, additional. So it will largely improve the carrier number, or it will largely improve the conductivity, electrical conductivity of the semiconductor. This is how when we add a pentavalent impurity, we get a lot of extra electrons. So the impurity atoms added provide extra electrons in the structure, and therefore they are called donor atoms. The electrons are majority charge carriers and holes are the minority charge carriers. Even if the there are a lot of electrons produced by the added impurity, there already exists few electron hole pairs, right? So there will be few holes available in the pure semiconductor. When we add some impurity, a large number of additional free electrons are available. So the number of electrons are much more than the number of holes. Therefore, electrons are called majority charge carriers, and we call that kind of semiconductor N-type semiconductor. So when we add a pentavalent impurity to a semiconductor, we get N-type semiconductor with large number of free electrons, much greater than the holes. Is that clear to you how a N-type semiconductor is obtained? Is that clear?
Yes,
How?
teacher.
Okay, by adding a pentavalent impurity, we can make a N-type semiconductor. Now let us see how a P-type semiconductor is formed. So as I told before, in silicon atom, they have 4 valence electrons and they share the 4 valence electrons with their neighboring atoms, and their octet is complete. Now suppose we are adding a trivalent impurity like boron, gallium, indium, etc. Here we have shown a boron, which is a trivalent impurity having 3 valence electrons added. So when we add a boron, what happens? 3 of its electrons get shared with the 3 of the neighboring silicon atoms. But it do not have enough electron to share with the 4th neighboring atom. So there is a vacancy of electron there. There is a deficiency of electron. Because it has only 3 electrons, it can share only 3 electrons with the valence, with the neighboring silicon atoms. It doesn't have the 4th electron. So the position of the 4th electron is vacant. What do you call a vacancy or a deficiency of electron? You call it a hole. So this hole can accept an electron from the neighboring atom. So from neighboring atoms, the electrons can jump to this position. So boron is called an acceptor impurity. So boron, which is the impurity, trivalent impurity added to the crystal lattice, will act as a acceptor impurity, and it creates a hole. So it can accept electrons from other atoms. So the electron jump to this hole, which means the hole will jump to the other position. So here, this is a vacancy for an electron or a hole. So from here, the electron can jump this vacancy and jump to here, right? So again, the electron is moving, the hole is moving in the opposite direction. So this hole acts as the charge carrier. So when you add around 10 raised to 8 boron atoms to a silicon crystal lattice, which has around 10 raised to 23 atoms per unit volume, a lot of 10 raised to 8 holes are produced. So the number of holes here are much more than the number of free electrons produced by thermal agitation or by the application of voltage. So holes becomes a majority charge carrier. So in an extrinsic semiconductor, which is obtained by doping trivalent impurity atom, like boron, gallium, indium, etc., to the pure germanium or silicon semiconductor, we can make a p-type semiconductor. And the impurity atoms added create vacancies of electrons, which are called holes in the structure and are called acceptor atoms. Why acceptor? Because it can accept a electron from the neighboring atoms. And the holes are the majority charge carriers and electrons becomes the minority charge carriers. Is it clear to you how we can make a p-type semiconductor? Is that clear to you?
Yes, teacher.
Okay, so thank you. Now we will stop here and in next class we will continue.